Okay, so this is our Physics 12 lesson. We're starting a new unit now. We're going to be looking at momentum and energy for the next little bit. So to start off today, we're really just going to do a quick review on momentum and impulse. Many of you are probably already familiar with these things, and if you kind of haven't remembered them, well, this will be kind of your review of what we should already kind of know from Newton's laws from Physics 11. Okay, so that's what we'll start with today. Okay, so we will start with, again, just a review of our definitions of momentum, impulse, just run through a couple of quick examples, and then we'll look at the momentum-impulse theory, the connection between the two, okay, and then we'll go from there. Okay, so when we talk about momentum, okay, just it's a started off situation, right? If the driver operating each of the vehicles above were to suddenly slam on the brakes, which would be the last to stop, right? So you have here A, someone's driving a train, B, someone's driving a car, and C, someone's driving a bike, okay? The one that's going to take the most time to stop is going to be the train. Reason being, okay, is that it's the heaviest and it would have been traveling at the greatest speed, most likely, okay? So the train has more mass, can travel at greater speeds than versus the car, which would have a smaller mass, and obviously the bike, which would have a smaller mass, okay? So when it comes to momentum, both mass and the speed, so their velocity, combine to give you an object's momentum, okay? So by definition, when we define momentum, the momentum is the product of an object's mass and velocity. Since velocity is a vector quantity, momentum is also expressed as a vector included direction. Now, I have forgotten to give an instruction with this. I'm going to send out an outline for this, but heads up, for this particular unit, I'm going to be asking you to kind of keep a running assignment going for every key definition and formula that we do. Okay, so as you go through the notes, you'll notice that certain words have been bolded and underlined. So any word that's been bolded and underlined, you're going to add to essentially like a vocabulary journal. Okay, and that definition needs to go in that journal, and then any relevant formula needs to go in there as well with like necessary units. Okay, that's just basically being done as an assignment that you submit to me at the end of a unit for just kind of like a check of like, thank you very much. I know that you've been, watching the videos. I know you've been taking the notes. I know you've been working on this kind of stuff. Okay, so that first one that you just saw with momentum, that would be the first thing in your vocabulary journal here now in like unit 3. Okay, so go back to that. All right, so again, momentum, it's defined as the product of an object's mass and velocity, and it would be a vector quantity, so it has to have direction. Okay, the formula for momentum there is then just going to be P, right? So the lowercase p is our symbol that we're using for momentum, is equal to m times v. You'll notice the arrows above showing the vectors, right? So velocity being a vector and momentum being a vector, and momentum is measured in kilogram meters per second. And your mass obviously is going to be in kilograms, and then your velocity is in meters per second. Okay, so those are your values there. All right, so let's just start with a relatively simple sample problem just to kind of review this again. Okay, so determine the momentum of a 3.00 times 10 squared gram hockey puck traveling across the ice at a velocity of 5.55 meters per second north. All right, so we do that. All right, so number one, we've been asked to find the momentum. We know the formula is momentum is equal to mass times velocity. We were given the mass of the hockey puck was 3.00 times 10 squared grams. However, we know that this formula requires this to be in kilograms, so we'd have to convert our grams to kilograms by dividing by 1,000, right? So that ends up equaling 0.3 kilograms instead, and we were given the velocity of the puck, which was 5.55 meters per second in a northern direction. So calculating the momentum is just a fairly straightforward, please multiply these two numbers together, right? So the 0.3 kilograms multiplied by the 5.55 meters per second, and you end up getting a value here of 1.67 kilogram meters per second, and the direction of the momentum is going to be the direction of the motion, the velocity there, right? So that would end up also be north. Okay, so that's just kind of relatively straightforward there. All right. So again, there's your solution if you wanted to see it in the slides, but it's the same kind of thing. All right, this would have been something we probably would have done in class, giving you 10 minutes to just kind of quickly review this to make sure you're all good. I'm not going to go over all of these right now. You can take 10 minutes yourself right now to just try these 4 problems. They're relatively straightforward, just making sure you're okay with that concept of momentum. Like I said, should be mostly review for everyone, right, when you learn Newton's laws in your dynamics units in Physics 11, but if it's not, take a few minutes, run through those questions, answers are on that slide, and then obviously send me an email if things are not working out for you, okay, or if you need more stuff with it. Okay, so then that brings us to kind of impulse, right, because there's a very important connection between momentum and impulse. We're going to go over that today as well in the same video. So when we talk about impulse is defined as the product of the force exerted on an object and the time interval over which the force acts. So essentially F net multiplied by delta t. Okay, impulse again is a vector quantity. Okay, because again the force would have been a vector quantity as well, and the direction of the impulse is the same as the direction that causes it. Okay, so whatever causing the force, right, whatever direction the force is acting in, that's going to be the direction that the force, that direction the impulse is as well. Okay, again, you'll notice that this is one of our bolded and underlined things, so this should also go into your vocabulary journal and with the following formula. Okay, the other thing you can use to define impulse, okay, oh wait, no, this is supposed to be my next slide. I moved this. Okay, skip that. Don't worry about that right now. That's supposed to be in my other set of slides. Sorry. Okay, so your formula for calculating impulse using that definition. Okay, so we can use capital letter kind of J here with the vector sign over top of it is again that force applied, right, or the net force multiplied by your change in time. Impulse ends up being measured in Newton seconds. Okay, think about what your units are for force, right? Your kilograms times meters per second squared multiplied by your seconds, right? What ends up happening is you end up just getting newtons and then multiplied by time, right? So obviously, force being newtons multiplied by time. There you go. Okay, so there's your formula. So again, quick little sample problem for calculating impulse. So a golf club exerts an average force of 5.25 times 10 cubed newtons in the direction of west. Sorry, that spacing just did not work out well. On a golf ball over a time interval of 5.45 times 10 to the minus 4 seconds. What is the impulse of that interaction? Okay, so we can do that one. Okay, so again, information we've been given. We've been given the force applied to the golf ball was 5.25 times 10 cubed newtons in a direction of west. We were given the amount of time it took, which was our 5.45 times 10 to the minus 4 seconds. We've been asked to find the impulse. So if we're going to find the impulse, and we know that it is the product of the force multiplied by the change in time, once again, we are just multiplying these two values together. Right? And when you multiply those two things together, you get a value of 2.86 Newton seconds. Right? And again, the direction of your impulse is going to be the direction of the force. So since the force was applied in a western direction, the impulse will also be in a western direction here as well. Okay? So just some very, very straightforward examples there going over impulse and momentum. We'll go through something a little bit more complex in the next little section, okay? But if you just want a couple more practice questions just on those simple calculations of, okay, well, can I calculate some basic impulse and momentum questions, then those are for you to take a look at, right? So there's 3 questions in your textbook. You may have already done them from Physics 11, but it's just a quick little, hey, do I remember how to do this? I'm gonna need to be somewhat familiar with these definitions and calculations as we move forward with this unit. Okay, so that leads us directly into the impulse-momentum theorem. Okay, so I've just defined both of those things with two different formulas. However, they are very much connected. Okay, so right, we talked about them as impulse is this, momentum is this. Okay, but there, like I said, there's a very direct link between the impulse and momentum given by the impulse-momentum theorem. Okay, and then start looking at a few more examples as well there. Okay, so again, here's your next definition, which is that impulse-momentum theorem, which is a relationship that states that impulse is equal to the change in momentum of an object. Okay, so we just looked at the straight definition of impulse, right, which was the force multiplied by the change in time, but you can also discuss impulse as just being the change in the momentum. Okay, and you would get the same value. So depending on what information you are given in a question, you may need to use an alternate type of formula here. Okay, so if we're talking about a change in momentum here, right, you can look at this concept of, okay, well, this would have been what we said our impulse was here, right, our force multiplied by our change in time. But we can say that it's just a change in momentum, and our momentum was defined as our mass multiplied by our velocity. Right? So again, if we're talking about a change in momentum, you're talking about what's the initial, right? The change from the initial to the final, or final minus initial here, right? So mv2, right? So this would have been momentum at the end of the scenario minus the momentum at the beginning of the scenario. Okay, and you would end up getting the same units there. Okay, so that's one way of doing it. Now this is where the slide was supposed to go, right? So another version of that formula is as follows. So another way you could write it here is that your change in momentum is the same as mass times change in velocity, right? Which is, again, because we're thinking, well, the mass isn't going to change, right? Even back from this formula, the mass hasn't changed. It's just your initial and your final velocity that changed. So you could technically just like factor out that m and talk about this as a change in velocity. So that change in momentum, right, delta p is going to equal m times delta v. Kind of remembering, all right, well, what's the relationship between acceleration, velocity, and time we have over here, right, where acceleration is equal to the change in velocity over the change in time. Rearrange that equation to get delta v by itself, and you just multiply both sides by delta t, and you get the delta v is actually acceleration times delta t. So we can substitute, instead of delta v here, we can call it acceleration times delta t. This is just all multiplication, which is commutative, meaning it doesn't matter the order in which we group them. So if we instead of bracketing these ones, we instead bracket the MA, well, that's our definition for our force, right? So there's our F net times our delta T, which is, again, that same thing that we had there for impulse in the first place, right, that we defined, okay? So again, we've got a few different versions of that formula, but they all can work out for us, right? So again, depending on the scenario, you can use which one of these equations or versions of the equations at some point of their derivation works best for the question that you're trying to solve. Okay, so let's take a look at a couple of these sample problems. Right, so in this first one, a student practices her tennis volleys by hitting a tennis ball against a wall. If the 0.060 kilogram ball travels 48 meters per second before hitting the wall and then bounces directly backwards at 35 meters per second, what is the impulse of the interaction? Okay, so let's try that one. We'll just start with A first. Okay, so again, in that first one, we were given the following. We were given the mass of the tennis ball. So the mass of our tennis ball is 0.060 kilograms. We were given the initial velocity, right? So VI or V1 was at a speed of 48 meters per second. And we'll just define that, we'll give that as a positive direction, like toward the wall being positive and coming back from the wall being negative, okay? V2, right, the final velocity would be on the way back, okay? So it was returned at a speed of 35 meters per second, and because it's being returned on the way back, we will have to assign that a negative, right, because it's coming backwards. So the question's asked us then, what's the impulse, right? So we've just kind of talked about how the impulse, it would have been force multiplied by change in time, right? But we don't have, in this case, we don't have the change in time, right? If we go back to the question, just to kind of recap it, right? We have speeds, we have mass, right? We don't have a change in time, we don't have a direct force given to us. So this is where we would then say, okay, well, if I need to calculate that impulse and I don't have force or change in time, I can instead use that version where, oh, well, impulse is actually the same, right? So a force times a change in time, right? So impulse being your force times change in time is also the same as the mass, right? The changes in its momentums, okay? So in that sense, we can use our mass, right, of our 0.06 kilograms. V2 was our minus 35 meters per second, and then we'll subtract, again, the mass of the tennis ball didn't change in this interaction, but the velocities did, so then that's being multiplied by the 48 meters per second, right? So you evaluate that, and what you get is negative 4.98 Newton seconds. Okay, and sig figs, it looks like we only get 2, so we'd actually have to round that to just minus 5.0 Newton seconds. And you notice that that value there is negative because it is asking about what's the force exerted by the wall, right? And the wall is what's sending it backwards, so that's why that value would end up being negative. Okay. All right, part B of that question is then asking us if the duration of the interaction is 25 milliseconds, what is the average force exerted on the ball by the wall? Okay, so again, what we can look at there is, so we're now given a change in time. So we've got that our delta t is now 25 milliseconds. So you would then have to divide that by 1,000 to get that into seconds. And we do have our force as well. So if we go back to this, right, so if we're solving kind of part B of this question now, where same idea, your impulse, right, is your force times your change in time, right? Well, we just solved for our impulse in the last question. What we're being asked to find is what's the force. So if I want to get F net, right, that force by itself, I just need to divide both sides by delta t. So the force is going to equal the impulse divided by the change in time. Okay, impulse was calculated. I'm going to use my non-rounded answer just to try and be as precise as possible, which is my negative 4.98 Newton seconds, and my change in time, right, my time given was 25 milliseconds, so you'd have to divide that by 1,000, and that gives you 0.025 seconds. Okay, so I'm dividing that by the 0.025 seconds, and you notice your seconds will cancel, and you'll be left with a value in newtons, which ends up just being negative 199.2 newtons. Right, there's my force exerted by the wall, and again, because it's by the wall is pushing it back in the opposite direction of its original motion, so that's why that force is considered negative. Okay, but again, in terms of sig figs, I only get 2, so I'm going to call this a nice negative 2.0 times 10 to the 2 newtons. Okay, so again, when you're looking at those questions on, okay, well, you're calculating impulse, or are you trying to find force, or are you trying to find certain velocities, right? Pick the formula that kind of works with the situation that you've been given, right? Knowing that there's a relationship between impulse and momentum. Okay, just because it says find the impulse and you're thinking, okay, that's the formula, but you realize you don't have anything in terms of force or time, well, that's when you kind of go, oh, right, I can also say that it's this. Right? And then all of a sudden you don't need force and you don't need time. Instead, you're just using velocities and mass. Okay, so depending on the scenario, use the one that that works. Okay, so there's that again. That's the same solutions, but let's look at another example here as well. Okay, so in this example here, you are given a 115 kilogram fullback. So this is a football question, right? So a fullback, a player on a football team, is running at 4.0 meters per second in the direction of east. And that fullback is stopped in 0.75 seconds by a head-on tackle. So again, this is still just dealing with all this happening in one dimension, right? It's just straight line stuff. We are going to obviously get into 2 dimensions in this, but just not today. Okay, and we're going to calculate the following things. We're going to calculate the impulse felt by the fullback and the impulse felt by the tackler. Okay, so again, if we want to try and set up, and then the third thing, we're going to calculate the average net force exerted on the tackler. Okay, so if we want to kind of think about what's happening here, switch back to my video. Okay, you essentially have this person here, right? This is mass 1, and it's traveling in this direction, right, at the speed that we've been given of 4 meters per second, right, going in that direction, okay? You have a second person with some other mass that's going to stop them in some way, right? Likely they are running at them, right? We just don't know. In this case, well, what's the mass of this person? We don't really know. We also don't really know what speed they're running at. We just know that they're coming in for a tackle, and it's a head-on tackle, okay? So we know that this mass here is the 115 kilograms. We know that they're running in that direction, okay? That's kind of the first scenario. Then what happens is that after that change in time of that 0.75 seconds, what ends up happening is that you have both of those masses collided, right, and their velocities are 0. They have stopped, okay? So if we start by looking at this first one, we're being asked, okay, well, what's the impulse felt by the fullback? Well, this is the fullback here, right? M1 and V, like this is representing our fullback with this particular speed, okay? So we're being asked for what's the impulse. So if we went to our original formula, our impulse is equal to the net force multiplied by the change in time, we kind of go, oh man, like, yeah, I guess I could figure out the net force here, right? Because if we think, okay, well, F net, that's going to be mass times acceleration. We can say, okay, well, I know the mass of the fullback, and I could calculate the acceleration, because the acceleration is going to be the change in velocity divided by the change in time. So I'm going to show you 2 ways to do this problem. So you could say, all right, well, that's mass times acceleration times my delta t. The mass of my fullback is 115 kilograms, right? My acceleration here, well, the acceleration is your change in velocity, so I went from 4 meters per second down to 0, right? So that would end up being, so VF minus VI, so it'd be this 0 meters per second minus 4 meters per second divided by a change in time, which is the 0.75 seconds. Right, that's your acceleration, and then you're going to multiply that by your change in time, which is your 0.75 seconds. And you quickly realize that, well, hold on, these guys cancel out, and then I'm just multiplying 115 by -4, right? And you get a value there of -460 Newton seconds. Okay, so, you know, that's one way you can do this. There is a slightly easier way you could do that, because we've already talked about the fact that impulse is also the same, it's defined as the change in momentum. And the change in momentum is the mass times the change in velocity, right? So that you can think about it as, okay, well, it's mass times change in velocity, or if we look at it specifically, mv2 minus mv1, right? Because really, if you can just factor out this m here, right, you get that mv2 minus v1, and that, by definition, is a change in velocity, right? Now, if we instead just used this formula right off the bat and didn't kind of worry about trying to find force, right, and said, okay, well, it's just mass times the change in velocity, right, or this mv2 minus mv1, we could have instead done, all right, well, my impulse is going to equal my 115 kilograms, my final velocity was 0, minus my mass of 115 kilograms, minus my initial velocity of 4 meters per second, right? That's nothing. Multiply your 115 by your 4, and bam, there is your -460 Newton seconds, right? So, ta-da. Okay, so again, 2 ways you can do it, but that works. Okay, so all that was for part A, where you were asked about what was the impulse felt by the fullback, and I guess we could either call it negative 460 newton seconds, or we could call it 460 newton seconds in the direction of west, which is the opposite of the eastern direction in which it was going, right? But by assigning, east as positive, then anything negative would be considered in a west direction anyway. Okay, so let's take a look at part B, which is then asking about, well, what's the impulse felt by the tackler? And there's actually not really a whole lot of calculation that we need to do here. It's just an understanding of our Newton's laws, right? Where this is basically saying, okay, well, again, we're trying to find the impulse, which is the force times the change in time. Bless me, right? And if we think about, well, the change in time is the same, whether we're talking about the fullback or we're talking about the tackler, right? So this is the same value. And the force is just going to be the equal but opposite value, right? Because we're dealing with them, right? One's going to be feeling the impulse in one direction, and one's going to be feeling the impulse in the other direction, right? So this is just going to be equal but opposite. So that force is going to be an equal but opposite force. Which means if we're going to take our equal but opposite force, we didn't fully calculate the force yet. We're going to do this in part C, but we don't really need to calculate it because we're being asked for the impulse, and whatever force this is just going to be the positive value of the one we already did, multiplied by the same value of time. So this entire value of the impulse is going to be the same, but just opposite. So this one would be just a positive 460 Newton seconds, or 460 Newton seconds in the direction of east. Right, that's what the tackler, the person who's stopping that person running east, is going to feel. They're going to feel that impulse in an eastern direction. Okay, and finally, part C does ask, what is the average force exerted on the tackler? Okay, so this is now asking us to find this value of F net. Right, so all right, no problem. So we have our formula. We have that the impulse is supposed to be 460 Newton seconds. We're looking for that force, and we know that that change in time happened in 0.75 seconds. So this just becomes a quick matter of dividing both sides by 0.75, and you get that your force is equal to 613 newtons. Okay? It's just kind of a combination of a few different use the formulas there. All right. Okay, so we've got another practice problem, but I think it's just probably better for me to just go through this one and then let you work through the worksheet and stuff on your own. So we'll do this one last example together, just again showing how we would kind of pick which formula we would use given the situation and go from there. Okay, so in this one here, what we have is a 1.30 kilogram ball is coming straight at a 75.0 kilogram soccer player at 13.0 meters per second. The player kicks the ball in the opposite direction at 22 meters per second with a force of 1.20 times 10 cube newtons. How long are his foot and the ball in contact? Right? So that amount of time where the force is being exerted on the ball, right, before it leaves again and turns around, what time is that? Okay, so again, if we're trying to find something in terms of time, we are going to need a formula that somehow involves time. So again, let's start with what we have, right? So we seem to have the mass of a ball, which was given to us as 1.30 kilograms. We have a mass of a player, which is 75 kilograms. We have an initial velocity, right, given to us as 13.0 meters per second. And again, that's the initial velocity of the ball. And we also have a final velocity, again, of the ball, which is going in the opposite direction. So we would give that a negative value of negative 22.0 meters per second. Okay. We're also given in the question the force at which the ball is hit. And that was a value of 1.20 times 10 cubed newtons. And again, that force would actually be a negative value, right? Because again, if we're assuming that its initial velocity of the ball kind of going this way, right? So like if this is the ball and then this is our player, right? This is considered our positive direction this way, and this is considered our negative direction this way. So if our initial velocity is going here, and then this guy kicks the ball and it goes this way, this would imply negative, right? That's why that velocity is negative, and will also imply that a negative force is applied in that direction. Okay? And again, ultimately, we are looking for delta t. Okay? So you might think, all right, well, I need a formula that involves delta t. Well, that's our impulse. And you might start with that and go, okay, well, impulse is going to equal my force times delta t. And you're like, all right, well, I need to find that, and I've got my force, but you actually don't know the impulse. So let's think, well, what's another formula for impulse we could use that we just talked about? And the fact that impulse is actually the same as the change in momentum, right? Which is the same as mass times the change in velocity, right? Or that idea of m times v2 minus m times v1, right? Or mvf minus mvi. So this is what's equal to our F net delta t. Okay, so what I want to do is figure, well, what is this value, right? What is that value of the impulse? So let's go and find it, right, using the fact that the impulse is going to be m times delta v. Noting here that the mass of the player is actually irrelevant right now, right, because we have no information about the velocity of the player, but we do have velocity initial and velocity final of the ball. So the mass being used in this equation is the 1.30 kilograms. And our change in velocity, right, is going to be our VF minus our VI. So it'd be negative 22 minus 13. Oh, this board is not big enough. Okay, so it's negative 22 minus 13. When you do that, you get a value of negative 35. So what you get is this 1.30 kilograms times negative 35 meters per second, right? So again, that was negative 22 minus 13, negative 22 minus 13, okay? Multiply those together, and you get a value of the impulse as negative 45.5 Newton seconds, okay? Now that you have that value for impulse, you can use it back in this equation here, right, to solve for your delta t, okay? So you've got a value of impulse, you have the force, you're solving for delta t, so your delta t is just going to equal your impulse divided by your force. Your impulse was your negative 45.5 Newton seconds, and your force applied was a negative 1.20 times 10 cubed newtons. Okay, and again, you should see that the newtons would cancel and you'd be left with something in seconds. And when you do that division, you end up getting a positive value, right, because your negatives would cancel, and you get a value of 0.0379 seconds. And we get 3 sig figs here, so if we want, we could actually write this as 3.79 times 10 to the minus 2 seconds. Okay, so again, just kind of thinking about those relationships and using a combination of formulas to get the information that you're needing. Okay, so what you've got to work on now then is that reviewed. So there was like 3 quick little textbook questions from just the quick review of how to calculate momentum, how to calculate impulse, and then up on Google Classroom you then have a worksheet to do. Again, the solutions to the worksheet are uploaded as well, and then again what I want you to be doing is keeping a running tally of like a vocabulary journal for this unit, and that will be something that will be submitted as a check mark to ensure that you are in fact keeping up with all of the work and all that good stuff. Okay, so all that's posted. Again, email me anytime with whatever questions you may have, and I will help as best as I can. Or again, as a reminder, if you're still struggling and emails don't really seem to be working, you can by all means request a Google Hangout, and I will do everything in my power to try and schedule something that will work for both of our times and schedules. Okay, and that's it.